Hello and welcome to the Citizen Science Training Modules. I'm Dr. Chuck Higgins from Middle Tennessee State University, one of the leaders of the Radio Jove project. Radio Jove partners with the Sunrise mission, and I'd like to acknowledge our contributors to these training modules as well as our funding sources. This is Training Module 1.0, Radio Science Background. The prerequisites for these training modules is essentially high school level reading and general science. In particular, scientific notation, the radio or electromagnetic spectrum, and reading and interpreting graphs of data. The learning objectives for today is to understand why we use radio astronomy and how does it compare with the visible sky, and learn some of the major discoveries we've made with radio astronomy, and give you a hint of what radio missions sound like from the Sun and from Jupiter. So first, why do we need radio astronomy? Well, in short, we can learn something new about the universe using radio astronomy. And to illustrate that, the pictures you see here show you the M81 galaxy group. On the left, you see it in visible light, and on the right, you see it in a radio map at 21 centimeter wavelength. This graph on the map on the right shows you that these three galaxies, which in the visible light you would think are independent of one another, in the radio map shows how the hydrogen gas connects the three galaxies, showing that they are tidally or gravitationally interacting with one another. The other images show you Jupiter in the visible and UV overlapped, so you can see the aurora in the northern hemisphere there, and what Jupiter would look like in the radio. There you see in the center what Jupiter would the thermal emission coming from Jupiter, but what you don't see in the visible is Jupiter's radiation belts, and the little dots on each side show plasma from one of the moons of Jupiter. So completely different view of Jupiter, showing us that Jupiter has a magnetic field and plasma and radiation belts trapped in that magnetic field. So really incredible way to learn something new. This is what the northern hemisphere sky would look like if we had radio eyes. This radio sky image was taken at 4.85 gigahertz from the National Radio Astronomy Observatory in Green Bank, West Virginia. The dots that you see here are not stars. They are radio galaxies and quasars from distances over 5 billion light years. The brightest regions that you see here are clouds of ionized hydrogen, and the faint rings that you see here to the lower left, these are supernova remnants. Both the clouds and the supernova remnants are within the Milky Way. You see, the universe looks completely different in radio waves, and that allows scientists to better understand the cosmos. This slide shows a few of the major discoveries that we've made using radio astronomy. For example, radio galaxies. The image at the top there shows you the elliptical galaxy Hercules A in visible light, and then added to that is a radio map showing these huge jets of energy coming from what is a supermassive black hole at the center of the galaxy. The image on the bottom there shows you the cosmic microwave background. So first discovered in 1964 using a microwave radio telescope, the cosmic microwave background is the leftover thermal energy from the Big Bang that occurred 13.8 billion years ago. Incredible. Other major discoveries: pulsars, pulses of energy coming from rapidly spinning neutron stars. Radio astronomy is used to discover planets around other objects called exoplanets, gravitational lensing, and finally, and most recently, images of supermassive black holes. So the figure on the right there shows you a combined radio wavelength image of the supermassive black hole at the center of the Milky Way galaxy. Have you ever heard the sun in radio waves? Well, this is what it sounds like. So what you see on the left is a frequency versus time spectrogram of many solar bursts, and the sound that you hear there, that increased volume, increased intensity over the galactic background of radio emissions, is coming from the sun. And the sound clip that you heard there is highlighted in the red horizontal line. And I played about a minute of the clip there. The graph on the right is the same event, but recorded at a single frequency at 20 megahertz. So you can see the difference between the spectrogram on the left and the single frequency on the right. You can hear live radio data streaming from one of our colleagues, Larry Dodd in Jasper, Georgia, on his YouTube channel. So you can go to that channel to hear what his radio telescope is sending out live. How about Jupiter? Have you ever heard the sounds of Jupiter radio emissions? Let me play you a little bit here.
Following is Jovian S-burst activity. Following is Jovian S-burst.
Those pops that you hear, those are tied to Jupiter and Jupiter's magnetic field. The cartoon there on the right shows you a picture of Jupiter and some magnetic field lines that run through the plasma torus of which the moon Io generates. So that's the electrons from which the radio waves are generated in a cone-like pattern. And the radio emissions that Radio Jove picks up from the Earth are called the decametric radio emissions, the DAM there. And so you see where those emissions are coming from. Now, if you slow those the sound file down by 128 times, this is what those little pops sound like. Each one of those pops that you heard before, when slowed down, has that whistling sound, and that tells us something about how the radio emission is generated at Jupiter. And finally, several images of what the sun looks like at different wavelengths. So the optical on the left and the H alpha emission lines from the sun, and then the radio map and what an X-ray map of the sun looks like. The radio map shows you the regions of high magnetic activity near the sunspots. And again, here's another solar radio burst. The graph that you see shows you a typical example of a type 3 solar burst, and the sound can help us identify that. Finally, here is a list of some great resources on basic radio astronomy, so I encourage you to check some of those out. There is an excellent list of resources here. Thank you for your attention, and next we will talk a little bit more about radio astronomy.